I welcome you to the session of Game Theory 3. You had learned how to solve a game with pure strategies, that is, how to solve a game whose payoff matrix was rectangular and of order m cross n provided that it had a saddle point. But in case there is no saddle point in the game, the payoff matrix was of order 2 by 2, then it could be solved by the method given in Game Theory 2. In other words, a game with mixed strategy could be solved when it was of order 2 by 2. But a game with payoff matrices of order m cross 2 or 2 cross n could also be solved easily with the help of the graphical method. The graphical shortcut enables us to reduce the original size of the game of order m cross 2 or 2 cross n to a much smaller size of order 2 by 2, which could then be solved by algebraic or shortcut method. Moreover, sometimes a player observes that one of his strategies is always inferior to at least one of his other remaining pure strategies, and accordingly he would not like to play that inferior strategy throughout the game. In such cases, the size of the game could also be reduced by deleting the inferior strategy from the game. Therefore, in this video, we shall be dealing with the techniques of reducing the size of a game to a considerable extent as and when it is reduced to an order of 2 cross 2. It could be easily solved then by the methods discussed in Game Theory 2. After going this, you would be able to reduce the size of the game of order 2 by n to that of a simple game of order 2 by 2, reduce the size of the game of order m by 2 to that of a simple game of order 2 by 2, apply the dominance property to reduce the size of the game, evaluate the value of the game after reducing the size of the game to 2 by 2. Now let us first discuss graphical method to solve a game of order 2 by n. The theory dealt will generally be applicable for any of the game with a 2 by 2 payoff matrix, but in case of payoff matrices of higher order, then we try to reduce if possible the size of the payoff matrix with the principle of dominance. And in case of a payoff matrix of order 2 by n or m by 2, we try to reduce the size of the payoff matrix to that of order 2 by 2 with the graphical method, so that the method discussed in earlier game 1, game 2 can be applied for finding the solution of the game. Now let us consider a game of order 2 by n by the graphical method whose payoff matrix is given by this. Since in the given matrix there is no one value which is smallest in each row and largest in each columns, the game does not possess a saddle point. Accordingly, the player A would resort to mixed strategies. Let the player A play the strategy A1 with the probability P, and hence the strategies A2 with the probability 1 minus P, since the sum of the probabilities of two strategies should be 1. Now we calculate the expected payoffs for player A against any pure move of the player B, that is against strategies B1, B2, B3 or B4 of player B. As B's strategy B1, then expected payoff is 2 times P plus 1 time 1 minus P gives P plus 1. If B's strategy is B2, then expected payoff for A is P. B3, then expected payoff for player A is minus 3P plus 3. Similarly, B4, then expected payoff for A is minus 4P plus 2. Now we plot the graphs of these expected payoffs for A, E1, E2, E3, A4 against P. For this we draw two particular lines at unit distance apart and mark a scale on each of them. The two lines A1 and A2 represents A's strategies A1 and A2 respectively, and the distance between these lines have been taken as unity because the value of the probability cannot exceed 1. We draw lines to represent each of B's strategies. Now to draw the graph of E1 P is equal to P plus 1, we put the value of P is equal to 0. So the probability of A2 is equal to 1 and E1 0 is equal to 1, which corresponds to the point 1 on A2 axis, and the probability of A2 1 minus 1 is equal to 0, and find the value of E1 1 is equal to 2, which corresponds to the point 2 on the A1 axis. Joining these 2 points, we get the graph of E1P. Similarly, we draw the graphs of E2, E3 and E4. It can be noticed that the points on A1 and A2 lines for the different values of E1, E2, E3, E4 of A's expected payoffs are respectively the values in the payoff matrix for the strategies B1, B2, B3 and B4 respectively. Thus, to draw graphs of E1, E2, E3, etc., we only consider the values in the payoff matrix for different strategies of B. Thus, to represent B's first strategy B1, we join 2 on scale A1 and 1 on scale A2 given in the payoff matrix for strategy V1. This line would represent the expected payoff E1P for the player A with P as x-axis and EP as y-axis. Similarly, we draw the lines of B's strategies B2, B3, B4 as given here. Now, according to the maximum criteria for the mixed strategy games, player A should select the value of P in such a way that he gets the maximum out of this minimum expected payoffs. The lower boundaries of the lines E1, E2, E3 and E4, that is the lower envelope, will give the minimum expected payoff, and the highest point on this lower envelope will then give the maximum of the minimum expected payoff. As shown in the figure, the lower envelope is shown by the blue line and the highest point is the peak. This is the lower envelope. The highest point is H, which is the intersection of the lines E2P and E4P, which corresponds to the matrix 1 minus 2, 0, 2. Thus, we have been able to reduce the size of the game from 2 by 4 to 2 by 2, and now the game could be solved with the help of the shortcut method. Therefore, these are the strategies for players A and B. Now let us consider another example. We have already discussed the graphical method to reduce the size of a game of order 2 by n to the order of 2 by 2. The method of dealing with the games of order m by 2 is similar to that of the game of order 2 by n. In case of the games of order 2 by n, we calculated the expected payoff for A for different strategies of B, while in case of the games of order m by 2, we will calculate the expected payoffs for player B for any pure strategy of player A. That is for different strategies A1, A2, A3 and A4. We discuss the following example. Let us solve this by graphical method. Since there is no saddle point in the game, the player B would resort to mixed strategies. Let the player B play the strategy B1 with probability Q, and hence the strategy B2 with probability 1 minus Q. Now the expected payoffs for player B for any pure strategy of player A, that is for any one of the pure strategies A1, A2, A3, A4 of player A, would be given by E1Q, E2Q, E3Q, E4Q. Now we plot the graphs. Similarly, we take B1, B2 and we plot graphs of each E, that is E1, E2, E3, E4 against Q, E1. As in case of game of order 2 by 4, we draw two vertical parallel lines called B1, B2 at a unit distance and draw the graphs of E1, E2, E3 and E4 against Q, as has been drawn in case of E1P, E2P against P. Now for mixed strategies, the player B should follow the minimax principle. And select the value of Q in such a way that he gets the minimum of his maximum expected payoffs. The upper boundary of the lines E1, E2, E3 and E4, that is the upper envelope, will give the maximum expected payoffs, and the lowest point on this upper envelope will then give the minimum value of the maximum expected payoffs. In this figure, the upper envelope is shown by a thick KLM and the lowest point L, the point of intersection of E1 and E3, gives the minimum value of the maximum payoffs of B. The point L corresponds to the matrix formed by E1 and E3. And the corresponding matrices of order 2 by 2. Thus, we have reduced the size of the game from 4 by 2 to that of 2 by 2, and the game could now be solved by the shortcut method. The mixed strategies for the players B and A are given by these are the differences. Now finding probabilities using shortcut method. The mixed strategies for the players B and A are these, and the value of the game is 3 by 2. We have seen that a game of order m by n or with m or n is equal to 2 and the saddle point did not exist could be solved by reducing the size of the game to that of order 2 by 2 by graphical method. Sometimes a payoff matrix of larger size where the saddle point may or may not exist can also be reduced by applying the principle of dominance, where certain rows or certain columns are carefully eliminated prior to obtaining a payoff matrix of the smaller size, so that the optimum strategies for the two players could be obtained with the methods already explained. The rule of dominance is especially useful for the evaluation of two-person zero-sum games where a saddle point does not exist. Now, the steps, the rules, general rules for dominance are: if all the elements of a row, say ith row of a payoff matrix, are less than or equal to the corresponding elements of the other row, say jth row, then the player A, maximizing player, will never choose the ith strategy, or in other words, the ith strategy is dominated by the jth strategies. If all the elements of a column of a payoff matrix are greater than or equal to the corresponding elements of the other column, then the player B, minimizing player, will never choose the column with greater values. Now let us consider the following example. Here player A has 4 strategies and player B has 5 strategies. The game has a saddle point at A3, B2 and the value of the game is 7. However, we shall reduce the payoff matrix by applying the principle of dominance. If we look at the columns of the given payoff matrix, we observe that the columns of the elements of the fourth column are greater than or equal to the corresponding elements of the first column. Therefore, the fourth column is deleted and the matrix is reduced by this. Now again, the elements of fifth column B5 are greater than or equal to the corresponding elements of the second column. Hence, by applying the principle of dominance, the fifth column being inferior strategies can be deleted and the payoff matrix reduces to this matrix. Again, we observe that the elements of the first, second and the fourth rows are less than the corresponding elements of the third row. Thus, the third row dominates all the other 3 rows and accordingly the first, second and fourth rows are deleted. Now the payoff matrix reduces to this. Again, the elements of the first column and the third column are greater than the corresponding elements of the second column. Thus, the second column dominates the first and the third column. The first and the third columns are deleted and we are left with the matrix. Yes. Thus, the solution of the game is given by player A should play with the strategy A3, player B should play with the strategy B2, and the value of the game is 7. In this example, we have seen that the matrix is reduced to a matrix of order 1 by 1, which corresponds to the saddle point. Thus, we infer that as and when a payoff matrix is reduced to an order of 1 by 1, we must have a saddle point. That is why we first look for the saddle point. Now let us consider the following payoff matrix is given for the two firms A and B. Using the dominance property to find the best mixed strategies for both the firms and find out the value of the game. The given game has no saddle point. If we look at the columns of the payoff matrix, it is observed that the columns elements of the first column are greater than or equal to the if we look at the columns rows of the payoff matrix, it is observed that the elements of the first row are less than or is equal to the second corresponding elements of the second row. Therefore, first row is deleted. Now, observing the columns, each and every member of column 1 is greater than or is equal to the corresponding values of column 2. Therefore, first column is dominated by the second column and we are left with the matrix this. Now applying the shortcut method. First step, subtracting values, interchanging values, dividing by the addition of both the values. We get these as the optimal strategies for the firms A and B and the value of the game. Now the general rules for the application of the dominance property has been mentioned, whereas a pure strategy was inferior to another pure strategy, but the dominance property is not always based on the inferiority of the pure strategies only. Sometimes a given strategy may be inferior to a convex combination of two or more pure strategies. As a particular case, the given strategy may be inferior to the average of two or more pure strategies. In such cases, if the given strategy is inferior to the average of two or more pure strategies, then the inferior strategy is deleted from the payoff matrix and the size of the matrix is reduced considerably. Thus, the dominance is not only recognized in case of pure strategies but also made applicable on the basis of mixed strategies. Since the average of two or more pure strategies is a case of mixed strategies, this type of dominance property is known as the modified dominance property. Let us use this modified dominance property as illustrated in this example. Consider a payoff matrix, two players with four strategies of each. The game does not possess a saddle point. The elements of the first row are less than or equal to the corresponding elements of the third row. Hence, the first row is dominated by the third row and the game is reduced to this. Further, the elements of the first row are greater than or equal to the first column are greater than or equal to the corresponding elements of the third column. Hence, the first column is dominated by the third column and the matrix is reduced to this. Further, in this matrix, the convex combination of the elements, that is average of the elements of the second and third column, are 2 plus 4 by 2, 4 plus 0 by 2, 0 plus 8 by 2, that is 3, 2, 4, and the elements so obtained are less than or equal to the corresponding elements of the first column. Therefore, player B would prefer to play the convex combination of B3 and B4 in comparison to his strategy B2. Accordingly, strategy B2 is deleted and the game is reduced to this. Again, the convex combination, the average of elements of A3 and A4 is 4 plus 0 by 2 is 2, 0 plus 8 by 2 is 4. Thus, the elements of the first row are equal to the corresponding elements of the average of A3 and A4 strategies, and accordingly player A would prefer to play the convex combination of A3 and A4, and as such a strategy A2 is deleted and we are left with the matrix of order 2 by 2. Now the optimal strategy can be found out by the shortcut method. Differences in rows and columns, interchanging values, and the optimal strategies are given by for player A 0, 0, 2 by 3, 1 by 3 and for player B 0, 0, 2 by 3 and 1 by 3 and the value of the game is 8 by 3. Now in this we have discussed this graphical method to solve 2 by n or m by 2 games and the dominance and modified dominance principle and their applications for reducing the size of a given game with or without a saddle point. Solution of a game after reducing the size of the game to that of order 2 by 2. Thank you.